Okay, why don't we start? Otherwise, we don't want to run out of time. If people join us once we've started, that's fine. So, for anybody who doesn't know me, I think everybody does, but just in case, I'm Simone Abram. I'm director of the Durham Energy Institute, and I'm absolutely delighted to welcome Nima today as our speaker. He's an assistant professor of sustainable and resilient infrastructure in the Department of Engineering, and he has a very multidisciplinary research portfolio, which I think we're going to hear a bit more of the products of today. Um, we the seminar will run, Nima will speak for 30, 40 minutes, and then we can have questions. So if you want to put questions in the chat as we go along, that's absolutely fine. And we can take verbal questions at the end as well. So on that note, why don't we get started? Nima, let me hand over to you.
Sure. Thank you very much. Hello, everyone. What I'm going to present today is called the anthro-physical design of built assets. A little bit of surreal kind of naming, but what it does is what I wanted to do. Okay. It has conceptually two components into it. The anthropic layer, the anthropology sciences looking into the human behaviors and stuff like that, and the physical part into it, which is looking into the physical characteristic of the asset. In here, it's just more of a naming scheme, but it's looking into the physical and functional as I'm talking about. But when we're looking to the building, let's say, for example, a hospital, and people inside the hospital together in order to design, this is how it looks into the problem. So what I'm covering today is saying how it's different from the other approaches, the more established design approaches out there, and what is different and how it's improved upon them. What is the science behind it? How it happens, and the methodology that we're using for doing this. Also, in the very end, I'm talking about two applications that I'm looking at. One is the improving the disease resilience in buildings, and for example, office buildings that I've already done a research on, or hospitals. It can be extended to other sectors as well. And also talking about the net zero buildings, which is my EPSRC and IA application has been based on. It's not future research, hopefully future research, so fingers crossed for that. And another topic that I'll be introducing at the very end. So how it's different, why we are having this kind of design scheme to be introduced. In the common design practices, we are looking usually at to identify the needs of an asset. So let's say we are civil engineers, we want to design a building. And what we need in the first place in terms of lateral load, for example, we want to see what is the load bearing capacity for earthquakes. So if like every 100 years an earthquake is happening in, let's say, Vancouver, BC, where am I right now, we have to know what is the intensity of that earthquake and how much load does it impose to our building in a 4-story building. Next, what we are doing is modeling the physical and functional characteristic of our assets. So we're saying that, okay, I have columns in these locations in the building, and they should be how wide they should be, how tall they should be, and how thick they should be in terms of their or what kind of material, what kind of grading for the concrete should I use in order to be able to bear all of those lateral loads imposed by the earthquake. Then when simulating the behavior of the building, let's say an earthquake is happening with the intensity of 6 Richters, and now let's see how our building is behaving with all of the physical characteristics that we are given. Let's see how does it behave, and where are the weak points, where are the extra, over design points or extra strong points, and then we are optimizing the characteristic of our asset. So let's say in a building, we're reducing the thickness of our columns in the upper floors and increasing in the lower floors. This means that we are reducing the weight of the building. We are reducing the total cost of material used, and we still absolutely fine with the lateral load imposed by the building. This is happening in many scenarios. For example, when we're designing the mechanical systems of the building, the HVAC systems, if we are looking into ASHRAE standards, they're looking into how many people in the building, what is the total room capacity, what is the size of the room, and what is the height of the room. Then you will be given a standard value for your ventilation rate in the building. So this is more often happen in many design practices in mechanical and civil engineering when we are talking about buildings. However, the critical point is where we want to simulate the asset performance in different scenarios. In here, we are looking to finite element method, for example, to see what is happening if the lateral load by an earthquake is given to the building. However, in many scenarios, like for example, seismic behavior that we are looking at, their standards are telling us what is the imposed load, lateral load of an earthquake. So we can do the design and we can see how much load is it imposing to the building or what will be the behavior. But in many applications, like energy behavior inside the buildings, the occupants in the building are affecting the behavior of the building significantly. For example, in a study, I think it was in 2021 in Australia, in university buildings, was showing that people inside the building, like the students inside the building who were using their classrooms or their project rooms and stuff like that, they have the potential to affect the energy consumption of the room by increasing the temperature in the thermostat or opening the window or stuff like this by 72% between the two extremes. And this is more significant when we are coming to residential buildings because we have more control over the building and we want to be more comfortable inside the building. So we are suiting everything based on our preference. So in this kind of context, the behavior of people inside the building is probably having much more impact on the building behavior, performance, let's say energy performance, as compared to how thick are the walls or where the windows are located, which are the physical characteristics of the building. Another scenario, another case study was the disease resilience of building. Back in time when the COVID was hitting us, I started the research by creating an open source agent Python library for simulating the behavior of people inside the building, and then seeing how does it affect into the energy disease resilience of the building or the infection risk of COVID-19. And I'll be talking about this research in more details, but it's significantly affected by what people are doing inside the building. We can fix the problem of disease resilience purely by behavioral changes. For example, our study showed that masks are not anything near to change of behavior. For example, for how many times you have to use the coffee place in your office, or time allocations like these can affect the disease resilience much more than any other more intrusive interventions. So what does the anthro-physical design practice do? We are taking the same 4 steps that we had, taking the needs. For example, in here, in terms of disease resilience, we are looking into the virus quantas allowed per cubic meter of air. There are standards out there. Medical sciences are telling us how much people can intake or inhale of viruses without getting sick. Then we are putting in the assets characteristics. Where are the walls? What is the total room area? What is the ventilation rate, and so on and so forth. We are looking into the simulation of the asset performance. But before then, we are adding one more step, modeling the occupants' social and personal behaviors with autonomous agents. And in the real world, let's say we are talking about a hospital setting and the disease resilience, a medical doctor who, after visiting every patient, they're washing their hands. So it's a personal behavior. And they're having a coffee with their peers like every 2 hours, 3 hours, or they're having a conversation with the head nurse in the corridor. So these are the social behaviors. So any interaction between the different people are social, any personal thing that happens and affecting the performance in the end is called the personal behaviors. And then we are simulating the asset performance, just as we have done earlier in the more common traditional design practices. And then we are determining the optimum characteristics. For example, here the optimum could be what is the optimum ventilation rate, not to waste any energy, not to increase the infection risk. So this is how it works, that the agent-based modeling that we are doing is creating somehow a digital twin of people inside the building. So what is the science behind that? It technically combines three different methodologies. The first one, the artificial intelligence. AI is, I'm talking about this as just being a little bit, too simplified sometimes, and everything is being related to AI. I'm using a different aspect of the AI as the chat GPT and stuff like this. Then we are using operational simulation, operational research. Agent-based modeling is technically in operational research. And then I'm using building information modeling in order to make a digital twin of the asset. So the first piece of the puzzle is the artificial intelligence. And generally speaking, AI refers to all techniques designed to mimic human natural intelligence. So today, the buzzword AI is mostly talking about machine learning and deep learning, which is the image processing or transfer learning, and all of these chat GPT or image recognition, video processing that we are looking, they're machine learning, and they're all a subset of artificial intelligence. They are not equal to artificial intelligence. AI is a more generic term which is being used, and it contains different methodologies. Human reasoning processing is something called cognitive maps, are very effective into modeling how people are behaving, thinking, or reasoning. The machine vision, which is the machine learning or deep learning aspect of AI, is also a subset of AI. Natural language processing, when we are talking to our Siri or Google, how does it understand when you're saying how rainy it is today? Do I need an umbrella today? And it's telling you, is it raining or not? So this is all natural language processing. This is not machine learning. And then we are having motion robotics, which is also a part of AI, how they finding a path, or like the Teslas, the autonomous driving in Teslas and other electrical cars is also, somehow related to this kind of AI aspect. So what I'm using in my research is called the granular computing, and it's an emerging field of AI. Very recently is increasing in size because it's now being joined by machine learning so much, and it deals with processing complex data structures, which are best represented as information granules rather than hard numbers. Fuzzy set theory is one component of granular computing, which is in anthro-physical design is being used. And to describe it more effectively, let's look into an example. Let's look into the occupant's energy behavior and how people are behaving within the built environment, let's say opening their windows and stuff like that, and how it's affect the building energy performance in the end. So when we are talking about, for example, opening a window, we are talking about the perception of temperature. So if you feel hot inside the building, you're opening the window for a breeze. So how does it happen? The perception of the temperature that we have, it's not a hard number. You don't feel that the temperature is 32.5 degrees. You feel hot, you feel warm, or you feel cold. So these are more subjectively expressed knowledge rather than being a very hard number, objective number. So what the fuzzy logic is doing, or for example, another probably disaster in decision making with the objective numbers is that, let's say we're having three ranges of perception of temperature, for example, cold, warm, and hot. And what happens to 3.5? if we want to do old school, the objective numbers, computer programming, it means that 3.5 degrees is as hot as 43 degrees. If we are not, introducing extremely hot, 30.5 is as hot as 43 degrees for a computer for your HVAC system control, and it means that it has your AC, for example, has to work full blown in order to reduce the temperature from by half a degree Celsius. And this is not efficient. Obviously, in reality, it's not like this. So what fuzzy set is doing is allowing us to make gradual transition between the different states. So 3.5 degrees can be 99% relevant or equivalent to warm conditions, and 5%, 1% compatible with the concept of hot. Or we can have something in between 50%, 50%, or 30%, 70%. So this is how fuzzy logic is working. It's allowing us to make the computer understand how people are perceiving the different conditions outside, or how people are, human logic works in terms of, reasoning with the conditions around them, surrounding conditions. So what's another component of the AI that I'm using is the cognitive maps. Cognitive maps are good for looking into the human reasoning process. And what it happens is that, let's say we're talking about the perception of temperature. There are so many factors that are affecting the temperature, our perception of temperature, plus they are affecting themselves. So for example, about the perception of the temperature, the wind speed is a very important factor. Feel like when you're looking at your cell phone, the forecast telling you what is the temperature outside and what does it feel like. That feels like is including the wind speed, the moisture, the sunlight, what time of the day is, what activity you're doing. Your cell phone is not including that, but all of these are affecting how you're perceiving the temperature. And they're affecting themselves as well. For example, the moisture and the sunlight and the wind speed and the temperature all of them are affecting one another. So in order to see how these complex structure of different factors or parameters are working and what I feel in the end, if I want to model the behavior of people inside the building, I have to be capable to look into what is this perception of temperature. I have to know at every time of the day how agent A or agent B is perceiving the temperature, and are they going to open the window, or are they going to turn the AC on or not? So in order to get this more accurately, we have to see all of these factors and their interrelationships. Granular cognitive maps is actually doing this. The cognitive maps is actually doing this for us by modeling these kind of interrelationship between these structures. And in theory, it's too simple. All of these links are simple statistical analysis. So one regression analysis between for example, wind speed and moisture is telling us what kind of concept should I consider. And then we are doing a lot of data processing by collecting a lot of data and seeing, okay, how the moisture and perception of temperature is affecting one another, or the wind speed and the combination of the wind speed and moisture and sunlight is affecting the perception of temperature. And the beauty of the granular cognitive map is that it is allowing us to represent each of these rather than hard numbers with those subjective states that I was talking in the last slide. So the perception of temperature can be hot, cold, or moderate. And then we can have the moisture being exactly the same defined. Or if you have, numerical numbers, objective numbers, for example, for the sunlight, how many luxes of sunlight are you receiving during the day? You can include the numbers in, the hard numbers in, or the wind speed. Very, very simple calculation from the forecast you can get in. You don't need to define everything with subjective numbers, subjective states, but we can if we need to. The second piece of the puzzle is the agent-based modeling, which is the operational research simulation. And these simulation techniques are designed to simulate the behavior of real world system over time. So the complexity or what they're offering is that this over time thing in here, that if we are looking into the machine learning, for example, they're set in order to predict something one off, like one at a time. The LSTMs are a little bit advancing in that regard, but not to the level that the simulation techniques are doing. The simulation techniques are dynamic, so unlike machine learning, which are static, we can see how people are behaving over time. So I can see the difference between day and night and day and evening time and what happens over the time or how the situation evolves as you're, for example, doing some workouts in your room in terms of the temperature of the room. So there are different methodologies for simulation. One of the oldest one, maybe it's outdated right now in many applications, is discrete event simulation. It's still used in manufacturing industry so much, and it's best suited for supply chain management and very effective simulation. System dynamics is for that is the system thinking that, at DEI we are thinking for the net zero. So it's a top-down simulation technique. I've been working with system dynamics last 12 years over. I started working with in my PhD, and then the granular cognitive maps is so much related to system dynamics concept. But the simulation that we're using in here is the agent-based modeling. So agent-based modeling is a very interesting, a very novel simulation technique, which can be either top-down or bottom-up. And it's looking into modeling the behavior of individuals inside, let's say, an environment, and then the overall performance of the system being captured from the interactions between these people. This overall performance can be disease spread between people or infection risk. So what the anthro-physical design is using, the anthropic aspect of it is using is agent-based modeling. So if we are combining AI and the agent-based modeling, we can look into making the autonomous agents or digital twins of people inside the built asset. Let's say I'm taking one of the humans out. We have to do this for every one of them, but let's say a normal age male, like between 30s to 60s, their active life, they're having personal behaviors and social behaviors. Their social behaviors are, let's say, they're going to meetings or talking with a friend or stuff like that. Their personal behaviors are how many times a day they're washing their hands, or are they wearing a mask or not? Are they vaccinated or not, or stuff like this. Then we are making the granular cognitive map in order to see how their behavior are being shaped based on their perception of the environment. And each of these are being defined by the fuzzy sets that we were talking earlier. So the weather can be cold, warm, hot, how they're perceiving the temperature. So this autonomous agents or digital twins of human are combining three different concepts. The granular computing for these identifying the subjective concepts, cognitive maps in order to see the interaction between the different environmental conditions and how people are perceiving the conditions outside, and then agent-based modeling in order to see now that I have a 30 years old man, 40 years old woman, two kids, and one elderly and one, for example, handicap in the building, disabled person. What is the overall conditions in the building, and what will be my disease resilience of the building or infection risk? So the third and last piece of this puzzle is building information modeling. And I'm literally not making any innovation in BIM. It's not a biggest strength of mine, but it's a very commonly used practice for making digital twins of the assets. It's very well established, so it's easily you can make the model of your building in the with BIM platforms like Revit or Tekla, and it serves like as a simulation environment for my autonomous agents. So that's only why I need the BIM to be involved. So what BIM is doing is storing all the physical and functional features of your asset. For example, it's the total area, the spaces, the height of every space is included. Where are your windows? All of these are the physical features of the asset. And the functional assets, functional features are like how strong is the ventilation rate? What is the, for example, texture of my window shades? What are my lights? These are the functional features. However, it's important to consider that BIM is a static modeling technique, so it doesn't see how everything is changing. For example, during the day, if my shades are smaller, the interior of the building will be much hotter than overnight because of the sunlight. But BIM doesn't see this. It's just telling you, it's storing all the information, all the features of the asset inside the database, and it can be retrieved whenever it's needed. We need to extract of these features in the anthro-physical design for the physical aspect of the design practice, and then that's why we are using BIM. So what it does is that, let's say for the physical asset, where are doors, where are windows, where are walls, where are HVAC system, and for example, the heat conductivity, the functional feature of the asset. So we're storing all the information about these features inside inside our model, and then we can extract them for the anthro-physical design. So we are having three components. The first one is the asset module, which uses BIM in order to get all the physical features and the functional features of the building. For example, the thermal conductivity of the walls and the windows, sound isolation, and the physical features are size, orientation, and thickness of the walls, for example. Then we have the occupant module, or the digital twin of human, anthropic aspect of the design. It's the social behaviors and personal behaviors are being stored. So sneezing, what is the breathing rate, what path they're taking are the personal ones, and the social ones can be the interactions with the others or the group talks or meetings. And then they're combined into the simulation, and we are taking two things into consideration: the human-to-human interactions. So if I'm talking to some colleagues in the corridor of my offices, for example, at Durham, that is called the social behavior. And this simulation is looking into that over time. For example, I'm telling my simulation model, the autonomous agents, every 2 hours, two random people, seeing one another in the corridors, and they're having a chat for 5 minutes. And it can simulate that, it picks two random people and then simulates their chatting in the corridors for 5 minutes and then release them. So this is how the human-to-human interactions happens. Then the interactions between the asset and people is being considered with both modules in. For example, if I'm opening a window, there is a new outlet and inlet for air, natural ventilation, and this is a human asset interaction. An agent-based model can also do this. For example, my agent is triggering every 20 minutes, for example, or 12 minutes. It's reassessing the perception of temperature. And if it's hot enough, I'm opening a window. And when I'm opening a window, I'm changing something in my assets. So the functional features of my assets should be updated as well. So these are being simulated over time, and this is how the simulation of behavior works. And then based on all of these interactions, there are some updates into the module. For example, if I'm opening the window, there is a feedback going into my occupant module. It's telling me that I don't feel hot anymore. It's rather cold outside, so I have to close the window. And it also changes something in the asset as well. And what I am doing is technically the novelty of my research is this human asset interactions. The rest is out there I have to make them in order to make this human asset interactions happen. However, the human to human interaction is agent-based, pure agent-based modeling. There are tons of studies out there looking into, for example, how it's affecting the disease resilience or how it's affecting the energy consumption in buildings and so on and so forth. The asset module or the BIM is being studied so much that you can see tons of studies out there looking into the functional design of, for example, HVAC system using based on the asset module. But what I'm doing and what my research is introducing through the anthro-physical design is this human asset interaction. So I think we can have a Q&A here before showing or maybe I proceed with my two applications, and then we'll have a question time. So the first application that I'm talking about is disease resilience, and that is something that the research has been concluded. We're looking into a further extension of the work, as I'm going to talk about, but the sustainable building design is still under development, and I'm still looking into that. So the case that was based on a recent project on improving what I'm talking right now is based on my recent publications in Sustainable Cities and Society under the name of Improving Occupational Safety in Office Spaces. And we got empirical data for an office in South Korea about how the COVID outbreak happened to be there. And I've developed an agent-based modeling engine in Python. It's open source. It's called CODIS. And it takes the functional characteristics of the building, the physical and functional characteristic of your building, and then you're defining a specific type of agent. And the limitation is that all the agents are the same right now. So all of them can represent one type of behavior. And it simulates how they're looking into the building. For example, this is an office building, and the animation here is showing that when they're coming to work, using the elevators, they're going to their offices, their desks, they're talking to one another, they are going to different places, they're having a coffee spots. If you're seeing my cursor right here, there are 2 coffee spots, for example, here for them. So they're showing, these are the meeting rooms. You're seeing, some of them are going to the meeting rooms once in a while, using the meeting rooms for having a chat or stuff like that, the washrooms and stuff like this. So it simulates the behavior of people in the built asset. And it also monitors how much air they're inhaling and exhaling. And when you're exhaling, and if you're sick, the red ones are the sick ones with COVID. So those red ones are exhaling some viruses quanta into the air, and that is being inhaled by the others. And when they're inhaling to a certain level, they're getting sick. So the way that it works is that getting the ventilation rates in the building, getting the architectural design of the building, and knowing where those sick people are at every point of time, we can see how much viruses they're exhaling and what is the density of the quanta of the virus in the environment. And this can tell us what is the probability of getting sick if you're spending more than 10 minutes or more than 1 hour in this location. And this is the accumulative probability. So we can see that this is the corridor, the elevators hall, which is a rather high risk location, and it makes sense because it's a common environment area that they're all using. These are the coffee spots that they were using, and you can see that it's much denser than the other places, and these are the meeting rooms that we're having. And our sick person, the 2 first infections, happen to be in the north wing of the building, and we can see the north wing is much more prone to infection as compared to the south wing because of over there more sick people, higher density of sick people. It means that higher chance of getting sick as well. And the interesting was that we had the empirical data, how many people was getting sick, where how every day how many infection has been observed every day through the test, and when the outbreak happened and they closed the building. So we had the daily data on the number of infection and when and where the first infected person entered the building. And we compared our simulation results to the empirical data, and it was interestingly close to the real data. And if I'm having, yes. Um, I'm comparing this into the presentation here to show how the different design practices work. But um, what we added was only the anthropic layer into the design. So with the ventilation rate, the simulation has been done, and it was pretty drastic differences in results that we are getting. This is show the airborne tool, which has been developed by Cambridge University. It's online through the link that I've given, airborne.com. And it's looking exactly this and looking to the problem that we've solved, exactly the same. The only thing is that it doesn't have any anthropic layer. There's no simulation, no overtime simulation. And it's only looking to the features of the building. How big is the room? What is the ventilation rate? What people are doing? So we have the ventilation rate here. We have the period of time that they're spending, the office hour between 9 a.m. to 5 p.m. We have the room size. These are exactly taken from the case study. And the occupancy, how many people are staying there, they're wearing no mask, and what they're doing, they're sitting, so the activity type. So there are many aspects of our simulation being involved in here. The only thing is that the interaction with the asset and one another is not being seen. And it's telling us that the infection risk in the entire office is 20%. And if we are taking a look back to our heat map in here, it's telling us, okay, in the coffee spots around 80%. If you're spending an hour in your coffee spots, most probably you're getting sick. But in here, it's less than 20%. And here in the North Wing, it's obviously more than 20%. So it's more granular information is given to us. And we can improve the ventilation, for example, in the North Wing. We can see that there are more people sitting there. So it's a bigger chance of people getting sick there. So better ventilation in here than here is needed, or more coffee spots in time when the outbreak happens. We don't want too few coffee spots in the building. So this is how different the common design approach and the anthro-physical is helping us to do. So we tested a few interventions, non-invasive interventions, like it's not vaccines, it's not masks. So adding a few more coffee spots. These were our initial coffee spots. There were 3 rooms or 3 by 2 rooms in here. Now we added them. We added a lot of them in here, and for example, we added dividers between the desks. So every 5 people, every 6 people have been divided. And the interesting piece was that just adding, for example, the coffee spots was reducing the infection risk more than introducing mandating mask in the environment. Or for example, these are in the paper, there are much more details about these interventions that we introduced, but we reduced the cluster size. So the total number of people sitting in each cluster is being reduced, for example, by dividers, the workspace allocation, the composition of the space allocation, the compression, the coffee spot, meeting room size to be increased in size, or the maximum number of people in the meeting room to be reduced. The duration of the meetings, we understood that the meeting rooms are a pretty high risk area to start with. So we said, okay, not more than 40 minutes or 30 minutes of meeting is allowed, constantly in this office. Maximum number of participants, working shift, and the enter and exiting window. This was also interesting, that just allowing people to arrive to work in a 60-minute window rather than to be specific at 9 a.m. for everyone and 5 p.m. For everyone. So we could reduce the infection risk in the elevator halls significantly by just making this change. And then we're introducing the face mask mandate and the vaccine mandate and seeing how these two are compared to the interventions that we introduce. For example, masking, we can see that this is the infection rate, not the risk or attack rate they're calling. So our attack rate was 50% when the outbreak happened and the building was closed. With the mask, we could reduce it into 28%. But with the interventions that we said, for example, reducing the cluster size and increasing the windows and also including the coffee spots, including more coffee spots, we could reduce the risk into around 0.06, not 7%, the attack rate. So, and this is the vaccination. So we can see that the vaccination that has so much controversy around it is still much lower, is still not very effective, not very, significantly more effective than what we could simply achieve with just reducing the number of people in the room or increasing the elevator halls and stuff like that. So this study that I want to proceed in the next one, in the next study that research that I want to introduce is to look into these concepts and implement it into the building energy behaviors and see how buildings are consuming the operational CO2 of the building, how we can reduce the energy consumption in the building. And the first thing that I want to tackle is the smart control of the HVAC systems, because HVAC systems are consuming almost 40% of the total energy consumption in buildings. It's even more in commercial buildings. And if we can reduce that, we can significantly reduce the carbon footprint of the buildings. So I'm not going into the details of the building energy modeling here because that is probably for another talk, but it's what I want to tackle in the commercial settings. First, I want to look into the airport decarbonization, how we can model the behavior of people, which is very simply hardwired because we have the timetable of the flight, and with agent-based modeling, I can tell you how many people will be in every hall of the airport and how does it affect the energy consumption, or the HVAC system should be more optimally controlled in order to reduce the energy consumption in the building. So I think this was my presentation for today. The references are here, but any questions, any comments, any express of interest for joining my research in the proposal for airport decarbonization is extremely welcomed.
Thank you, Nima. That was completely fascinating. So many potential repercussions, and yeah, hopefully.
Thank you very much.
Questions. I don't think we need to use the chat. If anyone's got a question, just either dive in or raise your hand or something. Please go ahead. It might take a minute for people to reflect on what they'd like to ask, but please
sure.
do.
Let me grab the chat box to see. Nothing yet here, but no.
Let me dive in then to ask you. I'm really fascinated by this, by the way that you're thinking about the behaviour issues and the human interaction element. The way you described it, it sounds like you are kind of taking what you know about the way that people move around and almost sort of characterizing that so that your model is saying random people might meet because we see people meeting in corridors and we assume that happens every so and so often. How do you do that kind of systemizing process from the sort of everyday, relatively random and routine things? How do you turn that into something that you can input into your model?
So what I have done in here is that the office behavior, there are some standards out there, especially in the United States, that how much time we're spending in meetings and how large are the meeting rooms. Or for example, how many times a day a normal person use washrooms, and we can make a random behavior to that. So because it's an average value that is given to us for example, from the standards. I can also see the outliers and every simulation time step, because when we're doing agent-based modeling, we have to introduce some simulation time step, which is equivalent to some real world, progressive procedure time precedence. So let's say my simulation, the infection risk is per minute. So at every minute, it says that every person has 0.0, for example, 4% chance of using the washroom. And out of those 200, they may go, to use the washroom. Or every minute, every person has the zero chance of 2%, for example, of leaving their desk and going to the coffee spot, because I know how many times a day or how much total time a day every person is using the compression areas in their offices. So it's something more into the probability theory that we are introducing the accumulative probability of every task and reintroduce it into the simulation by what is the probability now at every time step.
Okay, thank you. Thank you. That's interesting. So we've got a couple of questions lined up now. So first Kim and then Keiko.
Sure.
Thank you. Thank you for that talk. It was very, very, very interesting. I've got a question about something very specific, which is, and sorry, there's noise in the background. It's my dishwasher. The issue about the fact that occupants' behaviour can change predictions of building energy use by up to 300%. Like, that seems like a massive margin to me in terms of predicting behaviour. So like, what's the solution in terms of sort of trying to make sense of what the value of building actually is? Is it to model in that level of uncertainty, or is it to try and, I don't want to say persuade the occupants to behave in specific ways? So it might be slightly wider of your presentation. I was just trying to make sense of like, what's the solution to that? Because that seems like a margin that just can't be managed.
So something, and we should consider that it's an error. And the occupant's behavior can change significantly the building energy consumption. Mm-hmm. And as engineers, I'm talking about myself, that I am not here to change people behavior. I'm here to properly model people behavior in order to make an adaptable or suitable building for them. If we are looking, for example, energy retrofit of people who are doing a lot of workout in their rooms, and they want the room to be colder than any other space in their house. So it's the responsibility of the engineer to see that, and for example, change the insulation in the walls of that room in order to make more comfortable environment for them, rather than opening the window and then wasting a lot of energy. That's change of the energy behavior is coming, or the change of energy consumption is coming from the unfit design of the building in the first place. In many scenarios, if I'm opening the window while my thermostat is on in a building, it's technically a fault of the designers who are making your building too hot for the conditions. So, and there's no quick fix to that. If you're reducing the thermostat temperature, is taking 2 hours, an hour to get to your comfortable temperature. So you're opening a window. So what's the idea that I have is introducing is to making us more capable of controlling the building in the most comfortable way for the occupants, rather than changing the occupants to reduce the energy consumption of the building. We want to change the building in order to reduce to fit the occupants more. Does that make sense?
No, it doesn't make sense. So presumably once that kind of is a way of controlling their behavior, though, but like in an indirect way, because then they won't have to. So this is a simplistic way of, they won't have to do anything; they'll just exist.
Exactly.
Yeah.
Exactly.
Okay. Thank you.
And also, what I'm introducing in my application, EPSRC application, is that thanks to Simone, I've been contacted with Durham County Council, and we were introducing some part of the research to identify what are the major energy saving and energy wasting behavior for people. And for different characteristics or energy behavior, for example, templates. We're saying, okay, if you're an energy waster in general and you feel hot all the time, these are the things that you can do and reduce the energy consumption. This might be, in the end, helping to how to reduce the energy consumption or the behavioral change. But the main concern of my research is looking to how change the buildings in the first place.
Thank you. I was going to invite Keiko to ask a question, but I can't unmute him, and he doesn't seem to be able to unmute himself. So you might have to. I'm not quite sure why. But if you want to write your question in the chat, let's take Nora's question first while you do that.
Yep. No. Okay. Is it in the chat?
Nora's going to speak.
No, I'm here.
Okay. Go
on. This is fascinating. I come from an architecture background. I designed a hospital, and I have to say, I have a lot of clients who would probably have done a lot of things had they had those models to go off, because people love facts and numbers and little dots moving around on the screen and all of that. And I see a lot of, there's so much potential, particularly in this communicating between different disciplines. But I'm wondering, I think it's maybe a similar question that Simone asked, and maybe also similar to what Kim asked. And I'm wondering, is there space in those models for kind of cultural aspects of this behavior that you are kind of putting in? So, for example, and yeah, even cultural, and could I extend it to political? But so the standards you mentioned are mostly American, but so you would have to create, for example, a data set for a Myanmar context or Southeast Asian context. But then there are also those other aspects of, well, people don't want to, I don't know, be hot because they don't want to sweat, because sweat is not culturally acceptable. So it's also a level of yeah, how bodies are seen. And I wonder, are there can you put in infinite amounts of kind of parameters into the model? So if you were working with very, very closely, for example, with an anthropologist together in a particular environment, could you really create hyper adapted models for one specific hospital?
A very interesting question, and that is probably one of the key things in modeling is that we have to specify the scope of the modeling. So, and the scope is usually defined, but by how and to what extent the external parameters are affecting the performance that is of your interest. For example, the political issues in the country, which can make some conditions very stressful, that may affect the frequency of using the washroom of people. But to what extent? Probably 0.00005%. So we are having it line of the modeling scope and say, okay, anything beyond this is not of my interest because it's the impact on my system state is not important anymore. It's not significant anymore. And anything below that, I have to model. And for anything below that, yes, you can technically do this. This is a research that we are looking into with Professor Frank Cross in physics, that he has another agent-based modeling model, which is looking into the disease spread between the communities, so much larger scope. He's looking into macro scale, looking into the countries or states, or very large geographical areas. And my model is looking into more macro level and micro level and meso level. So if you want to go with very fine details of people behaviors, we are creating, let's say, 1,000 different prototypes of people. And then in the larger scale, when you want to replicate it, it's just to say that there are 20 million of these prototype and 10 million of these prototype, for example, in my community. And it tells you what is the more higher level social behaviors is being shaped outside. And also for more of, you raised something about, for example, Myanmar, or, if we want to get the other context data, if they are not readily available, that fuzzy logic piece is helping us to incorporate that into the model. The one that I showed here, it doesn't have any fuzzy logic. It's a pure numerical modeling, the disease resilience. It's very, I would say, simplified version of that, because it was I wanted as a proof of concept. But if my introduction for energy modeling is looking into that fuzzy logic piece, and then we can sit with people, do a questionnaire survey, and model their perception of, for example, temperature, using surveys, or what I am looking to do in the Royal Society application, which has been recently a semi-positive results, is to get the augmented reality cameras, headsets, and putting people in different conditions and allow them to select, for example, their preferred temperature for the environment. It has been proven that, for example, the color of light is significantly affects your perception of temperature. In very yellow light, you feel warmer than blue light. So we won't see how much significant is this condition.
Oh, thank you. I'm wondering if this Keiko's question is another aspect of this, because he's asking whether these are location and regional specific. So how regional variations that affect comfort in buildings might feed into your modeling.
So if you're looking to the two components, the physical aspect, you can literally import any IFC file from any building information modeling design into the framework, and it's telling you, it creates a simulation environment. So no dependency on the context. But for the behavioral aspect, for example, if we are looking to the behavior of people inside the offices, we cannot use that in the buildings anymore, in their houses anymore. So we have to stick into one context of the environment, but it can be changed or modified for a new context.
Thank you. We've sort of come to the end of our time, but I wonder if we could just take Jasper's question before we finish. It says,
could you adopt the agents to be vehicles? Yes, the agents can be anything. So you're defining, as long as it's a behavioral pattern inside them, and they can move around and they can change the environment or themselves, you can make all of that. And also, there's a very good one by Jennifer talking about how the CCTVs can be used, and that is exactly what we are looking at. I wanted to use the CCTV on the airport to see calculate those probabilities rather than sticking to some standards from other countries. See what is, for example, the average speed of walking for a normal passenger, or what is the average speed for going around the passport check lines or the border security lines and stuff like this. So all of these, yes, it can be a very useful platform in order to feed the design practice that we have.
Well, I think we should round off because we've run out of time. That was incredibly interesting, Nima. I think it's going to inspire a lot of future conversations. So you were saying if people might be interested to discuss those plans, I think we need to set
absolutely
opportunities.
Thank you very much.
Really wonderful.
I'm just writing down my email in the chat box, so I'll be more than interested to have a conversation about these, modeling concepts. So if we can have a chat, if you find that you can contribute anything to the project, I really appreciate if you reach out to me.
Thank you. And thank you
very much
for participating. And just to let you know, there is another, the next DEI seminar in, I think, 2 weeks. Do keep an eye on our, not LinkedIn page, what do you call it? Eventbrite page for details of seminars and public lectures coming up. So thanks very much.
Thank you very much. Have a good one.
Bye-bye, everybody.